Hello guys, so today we'll see the conic section. So today just see the basics of conic section and we'll see some of the applications. So conic section, or sometimes in short form we say conics. So conic section or the conics. Basically there are four basic curves, basic curve that are called conic section. They are the circle, parabola, ellipse and hyperbola. So they are something like this. The circle is something like this. Is circle, we know the shape. This is parabola, this is ellipse and this is hyperbola. Okay, actually this, if you recall this name parabola, this is parabola and this is hyperbola. They have difference, we'll see in detail, even though they looks like same, but actually they are different. So it's not the hyperbola is the two parabolas. Okay, so we'll see in detail what is the difference between parabola and hyperbola. Parabola and hyperbola basically was given by the mathematician, this Apollonius, one of the mathematician, and he gave the name parabola and the hyperbola. We'll see in detail that how come we get this parabola from the intersection of cone, double cone and plane. But now we just have we'll stick what is the basic application, or why we study this conic section, what is the use of this conic section, or what is the use of these four curves. One of the major application is in the astronomy. Okay, that is in the stars, planets, comets, that means heavenly bodies, and the path of these planets, comets or star, they all are one of the conic section. So the orbit of planets is one of the conics, one of this conic section, we'll see. So just like this, see, these are the solar system. So this is the sun, so here it's a sun. So about sun, these planets, these Mercury, Venus, Earth, they are revolving around the sun. And if you see about the path, this path, okay, this path about which these planets are revolving, they are the ellipse. So the path of orbits around which these planets are revolving, they are ellipse. So ellipse is also one of the conic sections. So until we know the detail about the ellipse, we can't determine the path of these planets, or how many days they take to revolve. So this is the sun, the Mercury, then Venus, Mars. So these are the 9 planets, and you can observe that as we move away from the sun, their shape is more and more elliptical. So now we also observe that the Mars, Mercury, Venus, and there's a comet also. Okay, so comet has either a elliptic nature or parabolic orbits. Comets are one of the heavenly body. Comets have either a elliptic nature, elliptic orbit, or they have also a parabolic orbit as well. So if comet has a elliptic orbit, as we see here, so as it has a elliptic orbit, it will move around the sun. If the comet has a parabolic orbit, so obviously it will just pass through the, so if comet has a, this is, suppose this is a sun, and if comet has a parabolic orbit, something like this, so it will come once and then it will move away from the, in case of parabolic orbit, we can say that the comet, so for a parabolic orbit, this is a parabolic, so suppose this is a comet, this is a parabolic orbit. So in case of a comet having a parabolic orbit, we say that the comet will just pass the sun only once and will never going to return, or it will never again come to pass through the sun. If it is an elliptic orbit, just like here, if it is an elliptic orbit, so see their path is very high, so maybe it takes many years to pass through the sun if the orbit is elliptical. But if the orbit is parabolic, so they will just pass to the sun at once and they will never ever return. So the comet, we can say the comet with parabolic orbit pass the sun once and leave the solar system. Okay, so if any comet has a path orbit, so it will be observed only once and then it will never ever going to come back to the solar system. Okay, so next we will see the path of projectile. So next let's see the path of projectile. Maybe it may be any spacecraft or any satellite. So the path of any projectile projected in a space, that may be a spacecraft or any satellite, so their path may be one of the conic section. Okay, so before understanding this path of projectile, let us see. We know that suppose this is any planet, let's say it is a Earth, and if there is any mass, let's say m, and let's say the mass of Earth is m, so there is a force of attraction between these two masses. The mass of Earth is greater than the mass of this body m, so this mass m will be attracted towards the Earth by the force of gravity that is given by G m by r square, where this r is the distance between the center of a mass and this body. This is r. Okay, so if any body or any spacecraft, any satellite, it is kept at some height h, so it will feel a force of attraction towards the Earth. Okay, now let's see, before understanding the path of a projectile, let's see what is the escape speed. Escape speed. So we know that if there is any, let's say, planet, suppose it's any Earth, so suppose we have any projectile. Okay, if we project with some speed, you know that it will go at some height and then fall back. Okay, this is how the thing happen. If we throw some stone or something, we see that after going to some height it will come back. But if we throw with such a speed that it is not going to come back, so that minimum speed is the minimum speed at which we will throw this body, this projectile, so that it is not going to back on the Earth. That is the escape velocity, or in formal definition we can say this escape speed, it is something denoted as VE, is the minimum velocity. So let's make it speed as a velocity because that is more. The minimum velocity which the body have in order to escape from Earth, in order to escape from the gravitational attraction. planet, let's say Earth. Okay, so if we are given some velocity, let's say if we are giving some velocity, let's say VE, so then it is not going, so it will be never going to come back. Okay, so this is the minimum velocity at which the body was projected, so that escaping from the gravitational attraction of Earth is the escape velocity. Normally most of the planets have some escape velocity. So for example, if you see the Earth, if we have a Earth, let's say Earth has a escape velocity around 11.2 kilometer per second. So if we project any object from the Earth at a speed around 11.2 kilometer per second, then it will never come back towards the Earth. Similarly, for Moon, if we project any object from Moon, so its escape velocity is 2.38 kilometer per second. Okay, so that means if any object is projected from Moon at, let's say 4 kilometer per second, then it will never come back. Similarly, so every planet have some escape velocity. Okay, so for example, if we have, let's say Mercury, Mercury has a escape velocity around 4.2 kilometer per second. Actually, there is why the values are decreasing or varies. You will see all these things in physics. There is specific formula to calculate the escape velocity that depends on the mass of a planet and the radius of a planet, and obviously gravitational constant. Okay. Next, to understand the path of a projectile, we need to have a orbital speed. There is something called orbital, that's orbital velocity. Okay, so what is orbital speed? Suppose from Earth, if any body at some height h, let's say from some height h, we are projecting with some velocity v. Okay, obviously if v is 0, so if v is 0, it will come back. So it will come back, okay, if v is 0. But if increase, so let's say I have increased the velocity a little bit more. So let's say some height we are projecting. So if we have velocity not 0, little bit more, so obviously it will try to move, try to rotate, but again it will come back and strike to the Earth. Okay. So if projected with let's say some horizontal velocity, it will fall back again and again. But there is some velocity, there is specific, we can say there is such a velocity, such a high velocity. So suppose there is such a high velocity, we are projecting with such a velocity, such a high velocity, such that this projectile is completing a path, a circular path. Okay, then that speed is known as the orbital speed. So again, understood? So let's have a formal definition for orbital speed. Understand orbital speed or velocity. Let's have formal definition for orbital speed, orbital velocity. So orbital velocity, it is the velocity with which an object, okay, any projected object, an object is projected such that it revolves around the planet, or let's say Earth. Okay, and if you talk about the Earth, for Earth, the orbital, let's say the notation is orbital speed. Orbital speed has a value around 8 kilometer per second. Okay, so let's say for Earth, we talk about the Earth. For Earth, the escape velocity is 11.2 something kilometer per second, and the orbital speed is around 8 kilometer per second. Okay. Now we'll see different path. We'll see the path of satellite or spacecraft as the projected velocity varies. Projected velocity vary. Okay. So suppose this is Earth, and from some height h we are projecting any spacecraft or satellite with velocity v. Now if v is 0, so what happens? If v is 0, it will fall down if v is 0. Okay. And if v is equal to v naught, so it will follow a circular path. So the path will be circular. This is one of the conic section. This is when velocity is equal to the orbital velocity. And what happens if velocity is greater than orbital velocity? And what happens velocity is less than orbital velocity? Okay. One more thing. If it is projected with a velocity is equal to, let's say, escape velocity. So it will escape from the Earth and follow a parabolic path. Okay. So in this case, if it is projected with a velocity is equal to escape velocity, then this is a escape from the Earth. So it will escape from Earth with parabolic path. So the path will be parabolic. Okay. Whereas in case of projectile is projected or spacecraft is projected at orbital speed, then they will revolve around the Earth and the path followed is a circle. So in this case circle, and if projected with escape velocity, then they follow the parabolic path. And let us suppose if they are projected at a, let's say, velocity is projected at a velocity. So in this velocity is greater than the orbital velocity but less than the escape velocity. In this case it will follow a elliptic path. This is elliptic path. Okay. Okay. Now what happens if it is projected at a velocity greater than escape velocity, and if we are projecting something with a velocity, let's say velocity is greater than the escape velocity, then again it will follow it will escape from Earth and follow a hyperbolic path. The path will be hyperbola. Okay. And next is what happens if it is projected, let's say at velocity less than orbital velocity. In this case also it will follow a elliptic path. Okay. So for different scenario, the for the velocity varies from 0 to escape and higher than escape velocity, it will have a different path. Okay. So again I am summarizing it. So if velocity is, let's say, 0, it will move down to the Earth. So it will, let's say this is the Earth. So if velocity is 0, obviously it will move down because due to gravitational force of attraction. Whereas if velocity is less than the orbital velocity, the path followed will be elliptic. Okay, the path followed will be elliptic. It may revolve around the Earth or it may strike to the Earth. We'll see. Next is if the projected velocity is, let's say greater than the orbital velocity but less than the escape velocity. Okay, so this is the blue one is the path in which the projectile or the satellite is projected with a velocity greater than the orbital but less than escape velocity. So in this case it will follow a elliptic path. Okay, and it will revolve. So elliptic path and revolve, and they will revolve around the Earth in a elliptic path. Okay, whereas if velocity is less than orbital velocity, the path will be elliptic, but it may not able to revolve around the earth, because sometime it may happen that it will strike to the earth and fall down. Okay, so it will, the whenever it will fall to the earth, it will, path will be elliptic, but since it has strike to the earth, it has intersected with earth, now it has no scope to revolve. Okay, next is if the satellite is projected at a escape velocity. Obviously escape velocity, the velocity at which the projectile will escape from the earth. So in this case the projectile will not revolve, it will escape from the earth, but the path followed will be a parabolic. Okay, what if projected with a velocity greater than escape velocity? So if it is projected at a velocity greater than the escape velocity, then obviously it will escape from the earth but follow a hyperbolic path. Okay, so summarizing it, velocity is equal to 0, it will fall down in straight line, no fall down in a straight line. Okay, if velocity is greater than, obviously greater than 0 and less than the orbital velocity, it will follow a elliptic path. Okay, and mind it, it may revolve or may not revolve around earth. If velocity is equal to the orbital velocity, it will have a circular path, and revolve around earth, revolve around earth. If velocity is greater than the orbital but less than the escape velocity, it will elliptic path and revolve around earth. And if the projected velocity is equal to the escape velocity, it will escape from earth. By the way, the path will be parabolic, so parabolic path, and escape from earth. If this is the earth, and if any body or satellite project velocity less than the escape velocity greater than the orbital velocity, or velocity is less than the orbital velocity, in both the case they will follow a elliptic path. Okay, so this is a follow the elliptic path. Yeah. So see, is projected with a velocity. Suppose this is some projected with a velocity. If velocity is less than the escape velocity but greater than orbital, it will have a elliptic path and revolve. Okay, whereas if you look at this one, okay, this is again the velocity is less than the orbital velocity and obviously greater, it will also have a elliptic path, but it may revolve, may not. The problem is that after going some time it will strike to earth here. So it is, if you look at closely, so it has, at this point it has strike to the earth. So if there would have been no earth, it would have followed the elliptic path, but because there is earth, so obviously it will strike there and come to the earth. Okay, so the velocity less than the orbital velocity, so it will follow the elliptic, but sometime it may intersect with the things. Okay, are you getting? So it will strike the earth. So the important part is that if velocity is less than the orbital speed, the path obviously will be elliptic. Okay, so if there were no earth, it would have fallen the elliptic path. So the velocity should be such that it should not intersect the earth, so path will be elliptic. But what happens if velocity is such a lower that the path such that path of ellipse, okay, in this case path of ellipse intersect the surface of earth, then obviously they will strike the earth. So we'll see in detail about how do we get these four conic section by the intersection of a plane, double plane and the double cone, and details of all the mathematical analysis. This was just the basic things. We're not going to see in detail about how the physics is involved. That is a part of physics in astronomy. You study in detail. But to understand why we are studying these conics, what is the use of these conics, just you should know that all heavenly bodies, whenever they revolve around each other, around some planets or around sun, they follow some path that is elliptic, circular, or if you are projecting any projectile from the earth, you will see that their path may be a circular, maybe hyperbolic, maybe elliptic. So you should know what path they are following. But before understanding what path they are following, we should be thorough with the concept of all the conic section. So we should know how to find these equations, how do we derive all the things. There are many concepts related to the conics. So we'll see in detail about the conics, but back in the mind you should know that whatever you're reading, whatever you're studying, it has a major application in astronomy. Okay.